We are reviewing the theory of VSEPR and Lewis dot structures. VSEPR stands for valence, shell, electron, pair, repulsion. Lewis dot structures are necessary for understanding VSEPR and the structure of compounds and ions. So let us begin.
Lewis dot structures are defined as two-dimensional structures of compounds or ions, which depict the bonding of compounds or ions.
Lewis dot structures show the distribution of electrons around the atom or compound. Lewis dot structures are drawn around the various chemical symbols for the atoms or compounds that are being depicted. They look roughly like this. There are different rules for how to do Lewis dot structures for single and multiple atoms.
For the single atom situations, one must first determine the number of valence electrons in the atom. Then you distribute them around it. Be careful though, you can only have two to each side of the atom for a total of 8, fulfilling the octet rule.
For covalent compounds, there is an entirely different process to go through. One must first determine the total valence electrons. Then one must determine the central atom. This is the one which is the least electronegative, and usually the first element in the formula.
One must then connect all atoms in the structure to the center atom. First you should connect with single bonds. These have 2 shared electrons. Then you should complete the octet on outside atoms. Then you should complete the octet on the center atom, except for exceptions which we'll go into later.
If an atom is still unsatisfied, which means that it doesn't have a full octet, then you must begin to use double bonds and triple bonds, which are drawn as 2 or 3 lines representing 4 or 6 electrons. Finally, you should double check octets and the total number of valence electrons.
One final Lewis dot rule that you should remember is resonance. Resonance is when one Lewis dot structure cannot show all the possible bonding formations in a compound. You should look for 2 or more atoms of the same element bonded to a center atom. Then show all the possible structures while keeping a fixed position.
As for exceptions, the exceptions to the normal octet rule of an atom having 8 electrons as the most stable form, helium and hydrogen only need 2 electrons to be stable. Boron and beryllium can have 4 or 6 and be stable. Phosphorus, sulfur, and xenon can have greater than 8 electrons. Now that Lewis dot is out of the way, we can move on to VSEPR, which stands for valence shell electron pair repulsion, and it is basically how to draw the different structures in 3-dimensional space.
To draw the VSEPR for a molecule, you have to first draw the Lewis dots like we have shown. After, you must determine the electron domains, which is how many bonds there are between the center atom and all other atoms in the compound. Then you should determine the arrangement of groups, which is determined by electron domains. After this, you should determine the bonding domains and the molecular shape.
The electron domains and arrangement of groups go like this. Electron domains consist of the single, double, and triple bonds, as well as the electrons that surround an atom in a compound. 2 electron domains form a linear arrangement, 3 form a trigonal planar arrangement, 4 form a tetrahedral arrangement. To find electron domains, you must count the total number of pairs of dots, as well as the bonds around the central atom.
This leads into the next step, that of bonding domains. Bonding domains are exactly what they sound like, the total number of bonds around the central atom.
There are certain ways to represent bonds in 3D. If you have 2 electron domains and 2 bonding domains, you make 2 lines for each bond and have the 2 bonding molecules opposite each other. If there are 3 electron domains and 2 bonding domains, then the 2 molecules are slanted down from the molecule they are bonded to and have 1 line for each bond. If there are 3 electron domains and 3 bonding domains, there will be 1 line to represent each bond and 3 bonds each separated equally from the central atom.
If there are 4 electron domains and 2 bonding domains, the bonding atoms will be slanted down and have 1 line attaching it to the central atom. If there are 4 electron domains and 3 bonding domains, there will be 3 bonds represented by 1 line each. 1 line will be pointed toward you, another facing away from you, and the last facing at the neutral spot. If there are 4 electron domains and 2 bonding domains, there will be 4 bonds, and they will be represented by 1 line each. 1 bond will be facing up, another coming towards you, another facing away from you, and the last neutral slanted down. These are the ways to draw the 3D bonds.
Nonpolar covalent bonds are bonds pulled equally and share electrons equally. A polar bond is a covalent bond between atoms when the electrons are shared unequally. The more electronegative atoms have slightly negative charges because they attract electrons better than less electronegative atoms. The less electronegative atom in a bond thus gains a slightly positive charge. A molecule that has one side with a slightly negative charge and the other with a slightly positive charge is called a polar molecule.
Dipole interactions occur between polar molecules. When slightly opposite charges are close to each other between two polar molecules, there is a slight attraction between the two polar molecules. Weaker dispersion forces happen between nonpolar molecules. When the electrons in two nonpolar molecules are located on the side near the other nonpolar molecule, it causes the electrons in one of the molecules to repel and move to the other side of the molecule. After this has occurred, there is a slight attraction between the two molecules.
For practice problems, do the Lewis dot and VSEPR for CCl4, then make the 3D drawing for it. If you use the Lewis, VSEPR, and dot rules correctly, you should get something that looks roughly like this.
And that is how you form Lewis dot and VSEPR.